Hi, everyone. My name is Suman Karamuri. Thanks for having me here. Today, I'm going to talk about distributed tracing at Pintrace. So a little bit about me. I'm a software engineer on the visibility team slash storage team at Pintrace. I'm very passionate about observability, monitoring, distributed tracing, and cloud infrastructure in general. So previously, before this, I was at Twitter. I was the lead for a project called Zipkin, and that's open source distributed tracing project. And before that, I also worked on for a lot of Silicon Valley companies like Twitter, Facebook, Amazon, Yahoo, and so on. So the motivation for this talk is let's see why we built distributed tracing at Pintrace, right? So at Pintrace, we care about performance. We want to know we want to make our service really fast and really engaging for our users. And the faster the service is, we notice that the more engagement it drives. So we care about performance quite a bit. However, just like all companies at this scale, our backend infrastructure consists of hundreds of microservices. The problem with if you have hundreds of microservices is understanding what's slow is one of the hardest questions you can ask in this system. So understanding why a request is slow, to answer that question, you need to understand how a request executed, and understanding that is very hard. So what do? Just like everyone else, we started with using metrics, right? Metrics are pretty cheap. It's just a counter in your service or some other latency histogram or something like that. And it allows you to aggregate your events at a host level. Once you have those events at the host level, you can put them on a dashboard to see trends. You can have alerts on them. You can combine these aggregates across all the hosts in a single service, mix and match them, and get a service level overview of what is happening. However, this system, the metrics do not tell you how requests are related to each other. They can tell you that, hey, like this request took X amount of time, this request took Y milliseconds, but it won't tell you how this request is tied to this other request, and if there was a causal connection between them. And that is the kind of information you need to understand why something is slow or how different requests are related to each other, right? So just like everyone else, we said, okay, let's use logs for this, right? So with logs, you can record discrete events, and they're very flexible. You can log whatever you want. Okay, so you can put a transaction ID in there or a request ID in there, and you can just grep for your logs based on request ID, and using manual correlation, you can understand how a request executed, right? So this is great, but this approach has a few issues. First of all, logging is very expensive, both in terms of producing those logs, processing those logs, storing those logs, and searching those logs. And most of the time, the correlation is manual. And the worst part about logs is, while they are very flexible, they can be very brittle because you are relying on developers to go in and add the information you want to see. And if they forget that or delete that information, you can't use them for understanding how a request executed or correlating different parts of the request. So what do? So what we did, the next step was we did what is called manual tracing. So what did we do? We took a bunch of very experienced engineers in the company, gave them our logs, gave them our metrics, gave them the code, and told them, hey, figure out why this search API is slow, right? So, and we named the project Project Prestige just to make it sound something like awesome. And the outcome of Project Prestige was these senior engineers spent about 2 quarters worth of time going through every single path in the search backend, and they were able to reduce the latency by 50%, right? How did they do this? They didn't do anything crazy. They just figured out that, hey, like we shouldn't be calling the spam service when we're doing search. So they removed the spam service, and they removed calls to a couple of other services that were not needed. And then our search backend was like 50% faster. But this approach doesn't scale because you have to keep doing this for every release. And also, it is very expensive. You are taking the most senior engineers in your company and putting them on this manual tracing project. This process is not repetitive, and it needs a lot of skill. So what do? We decided to build a tool so we can just give this ability to everyone, right? So our first attempt was building a tool called Pinpoint. Pinpoint was a single service tracing solution. It would trace a request within a single service using network calls, right? It was okay. It kind of told us what the problem is, but it was still not good enough. So once we knew that this was not working and not very useful, we just decided to do full-on distributed tracing, right? So what is distributed tracing, right? Let me give you a high-level overview. Distributed tracing is nothing but you record the events in a request in causal order. So if you have a request, you record the events that are happening on the request in the order they happened, right? So that's all distributed tracing is. So what do we do? Like, what is an example of this? The example is, let's say you have a simple service where you have a client that's talking to a service 1, and then service 1 in turn talks to service 2 to get some data, gets the data from service 2, and does some post-processing and returns to service 1, right? Very simple interaction. So let's see the events in this interaction, right? So let's say at time t1, you have, let's say at time t1 for this request r1, the client sends a request to the server. At time t2, the service 1 gets the request. And then it does a child request to service 2 at time t3. At time t4, service 2 gets it. At time t5, the service 2 has done its job and it returns a response to service 1. And at t6, the service 1 gets the request. And at t7, the service 1 does some post-processing, returns the response to the client, and at t8, the client gets the response, right? So these are the events in this request. So distributed tracing is just taking these events and putting them as annotations, spans, and traces. That's all distributed tracing is. So what is an annotation? Each event in this request is an annotation, okay? And what is a span? A span is nothing but a logical collection of events. So here we define a request response pair as a logical collection of events. So here, since we have two request response pairs, we have two spans. There is a red span and a green span. And because spans need identities, we just give them numbers S1 and S2, right? And a trace is nothing but a directed acyclic graph of spans. So there is a parent-child relationship between spans, and the way you assign that parent-child relationship is you just make one span the child of other. So in this case, the span S2 is the child of span S1. And this graph of spans is what we call a trace. So distributed tracing in this sense is just a fancy structured logging. So I sometimes refer to it as structured logging on steroids because it's just you are logging structured information, but you're also adding some metadata about the request and some parent-child relationships. So this is just a fancy form of logging, right? Now, what is Pintrace, right? Pintrace is the same idea of tracking this request and recording the causal events on a request across our entire infrastructure. We wanted to trace our request right from the client all the way to a database call. That's what we wanted to do across our entire backend. And for this, we built a zipkin-based tracing solution. And this distributed tracing in general is much more expensive than logs and metrics because you are doing a lot of additional work to track a request across services, and you're also logging a lot of metadata, right? So later I'll tell you how we solve the cost part of this, right? So I mean, we all come to conferences, we look at a tracing talk and say, hey, like this is awesome, let's go build it, right? So we were like that too. So here I'll talk about 5 challenges we faced when building the system, right? So if you're trying to do distributed tracing in the large, you are likely to hit with these challenges as well. So the first challenge you would face when building a distributed tracing infrastructure anywhere is you have to build up the instrumentation. One of the things with building distributed tracing instrumentation is it's hard and tedious. It's hard not because you have to write a ton of code, but you have to instrument those parts of the code which you usually take for granted. You usually have to instrument like some low-level HTTP middleware in your web framework, or you have to understand how threading model works in your web framework or something like that. Once you understand that, adding the instrumentation is as easy as just adding a log statement. So that's the hard part, okay? Then the tedious part is once you have to do this for every language, framework, thread pool, and protocol combination. I'll explain what that is. So let's say you have a Python application that's using Flask, right? And let's say Flask uses a certain thread model. So you have to build an instrumentation, a tracer for Flask using that thread model. And if that Flask app is communicating downstream with another HTTP service, you need to take that request ID and put it on that HTTP service. If you are communicating with a MySQL client, you have to take that request ID and put it on the MySQL client. If you're communicating with Memcache or a thrift service, you have to take that request ID and put it on the thrift service, right? And you have to do this for if you're using Django or some other framework, you have to repeat this process again. And if you are using a different programming language like Go or Java or Elixir or any of these other languages, you have to repeat this process for all those languages. And the worst part is if you're tracing a request across these languages, you cannot have a gap, because if you have a gap, your tracing request goes to that point, and then after that you can't trace at all, even though instrumentation exists down the line. So this is the tedious part of tracing, like completing tracing every single request in that path. So if you have a homogeneous infrastructure, this becomes easier. Or if you are using a framework that is already instrumented for tracing, it's really easy to do. So luckily for us, our main stack is Python and Java. And for Java, we use this open source library called Finagle, which comes with excellent tracer built in. So for Java services, we just take advantage of the Finagle tracer that comes with the library. It actually tracks requests over, it can trace requests over HTTP, thrift, and it also takes care of instrumenting the Memcache protocol, MySQL protocol. It actually, if you have multiple threads or thread pools or whatever, it actually traces through those threads and thread pools. So it makes it's an excellent tracer. So for Java, that solved our problem. For Python, we have our own custom in-house web framework. So for that, we had to build our own custom tracer using the Open Tracing API. We had to also build custom Android and iOS tracers because there are no known tracing solutions for those parts of the stack. So once we built the instrumentation, that solved one challenge. Then the next part was using these tracers that we built, we were able to get the spans and traces that we saw in like the first diagram, right? Now we need to collect these spans from all these services and store them somewhere so we can look at them, right? So the next step was to build a report and aggregation pipeline. So what do? Is we built these specific loggers, which would take the generated spans and log them to a local file. Then we have this tool called Singer, which reads the spans from the local file and writes them to Kafka. This pattern existed when we started the project. Singer was widely used across services, but Singer was never used across our entire infrastructure. So once we wanted to deploy Singer across our infrastructure, it created a few issues. First of all, we had to deal with security issues. We had to deal with operational issues because some tools deployed with masterful Puppet, some with masterless Puppet, some did their own thing, and getting the instrumentation, getting the Singer into all those pieces was a very big challenge. And finally we did it, and once we did it, we have hit another bottleneck, which was we have about 50,000 hosts, and all these hosts now start writing to Kafka pretty much constantly, and Kafka couldn't, Singer was not tuned for that, so we had to change Singer a little bit to make that work. So we built the first company-wide event aggregation pipeline as part of this project, which was very illuminating for us. Then once we had the aggregation and report pipeline, the next step was deploying our instrumentation to all the services. This in itself was a big challenge. We built roughly 3 instrumentations across 3 stacks, and we had to get this instrumentation into services. To get this instrumentation into services, we had to roughly deploy 100+ services. And to deploy this instrumentation across 100+ services, we had to work with roughly 40 teams. And the next challenge was, now I told you, remember, that tracing was expensive. One of the problems was when you're actually deploying this tracing across all these services, you just cannot trace all the requests. That would just bump up our infrastructure cost by 20% or so. So to mitigate that, what we did is we built this small piece called Sampler in our mobile app, which would sample the requests that we would trace. And currently, we sample at about roughly 1% of our traffic. And by doing this, at this rate, we were able to balance the quality of the trace, where we were able to capture more or less the data we want to capture, but with the least amount of overhead as possible. The other big challenge with instrumentation was that when we deployed it, there were some services that were super latency sensitive. We had one service which was looking up a cache and returning a number to the user. So because it was just returning an integer, it was doing very little work, and it was tuned for that use case. But once we deployed tracing and we were tracing a few requests, the amount of overhead generated by my trace was an order of magnitude more than what the service was doing per request. As a result, we had to work with the team to tune the service for these use cases and tune our tracer to fit those super low latency use cases. And there are several services across the company that have a slow cadence to deploy this, so we had to work with them to deploy this. It was mostly PM work, but somebody had to do it. And the other challenge was, whenever you deploy your piece of software with somebody else's software and something goes wrong, the first thing they'll do is they'll blame you. And that's a super big challenge. And you just have to deal with it and just tell them that, prove to them that your code is not at fault, and then they'll just go look elsewhere. So once you deploy the instrumentation, you start the sampler, you start tracing, you get all your traces in Kafka. Right now, we need something to collect the traces from Kafka and put it in some kind of storage. So what we did for this is we wanted to use the open source Zipkin backend to take the traces from Kafka and ingest them into Elasticsearch. But unfortunately, the open source Zipkin backend at that time did not scale for our needs. So that was one problem we had. The second problem we had with our system was that we were using a really old version of Finagle library, and it had some known bugs in the tracer, and the spans generated were slightly wrong. So we had to fix them up. And we couldn't do this with the open source system either. So what we did was we wrote a Spark job, which would read the spans from Kafka, fix them up, and then store them in Elasticsearch. And once we are done with this, we spoke with Adrian Cole, open source Zipkin maintainer, and then we contributed the code to him. And he, now the code lives under the Zipkin Spark streaming project in OpenZipkin project. So this Spark job actually aggregates the spans, constructs traces, sticks them in ES, right? That's our trace processing and storage pipeline. And once the data is in ES, we have to allow the users to look at it. So for this, we just took the stock Zipkin UI and configured it to talk to our Elasticsearch cluster, through which our users can access these traces. There were a couple of problems with the stock Zipkin UI. One thing we wanted was we wanted favorite traces. For example, if we see an interesting request, we wanted to say, hey, like this is interesting, keep this forever, right? Keep this trace forever. Otherwise, we'll delete all our traces after 10 days. So what was happening was the Zipkin UI didn't have this feature, so we had to build it ourselves. So it's not so much stock Zipkin UI anymore because we had to build that feature, and we did a couple of tiny UI enhancements, which we are in the process of contributing back to the community. And the Zipkin UI is good for searching through traces and looking at a single trace, but the Zipkin UI does not have any trace aggregation capabilities. What I mean by that is if you have to look at aggregates of traces and then get some insights, like which service is slow or any kind of trending information, Zipkin UI doesn't have those facilities. So for those use cases, we actually built our own in-house toolkit to analyze these traces. For the last bit, we actually recently wrote a blog post about it. You guys are free to go look at it. It's on our engineering blog. So, okay, so now that we have our traces and we can search and see our traces in Zipkin UI, and we thought we were done, but we were wrong. The reason was once we had the traces in the UI, what we realized was traces are just data. You actually needed software engineers to use that data to get the insights they need, and they need to use that data to answer the questions. And this was like a very important realization for us because most people think that once the traces are in Zipkin, it's done, but that's not the case. We had to do a lot of evangelism, and we had to do a lot of we had to bring a lot of awareness in our developers to actually use these traces effectively. And we, like in some cases, had to sit with them and show them, explain to them what the trace was, and how to use it. And once they saw it and they got it, they were like, they were mind blown. They were like, okay, this is so awesome. I just want to use it. How did I live with this? How did I live without this all these days? Was some of the feedback we got. So, yeah. So traces are just data, right? So I'll talk about how we use these traces to understand, debug, and tune our distributed systems in day-to-day, right? So let's start with like something simple. So one of the things we needed to understand was nobody in the company understands how a request executes. Like nobody understands what the heck is going on. So the first thing traces helped us was understand how a request is executed. So here we have the header for a single trace. In this header, you would see a few things. First thing you'll see is the duration. This trace took 500. This request took 581 milliseconds to execute, and the services shows how many services we hit. Here you can see that this request hit 36 services. Generally, a request in Pintrace hits anywhere from, for home feed, a home feed request hits anywhere from 24 to 48 services. The depth of one shows that if you call a request, that service is calling another service, which means that that service is, our architecture is pretty shallow, which is good because we are not doing too many network hops. So that's what the depth tells you. And the total spans tells you how many requests were made, because currently we only track the network requests. So the total number of spans in this case actually tells you how many network requests were made as part of processing this request, right? Then the next set, those blue boxes you see, are actually the list of services we hit, and also there is a name and there is a small x and a number, right? So the small x and a number is the number of times that service was hit as part of this request. For example, if you look at line 2, the graph service was hit 20 times as part of this request, and 17 of those times was hit by, it was called using the graph service client. Just by looking at this trace, till that point, we were unaware that there was a call to graph service that was being made without the graph service client. We didn't know people were calling not using the graph service client. This trace told us that, gave us that information, just one trace. And there are like lots of little things like this we figured out, but for us this was very important because all those non-standard clients were not authenticating correctly. They were not like, there were some scripts, or they were part of really old code or something like that, and we had to get that out. So that's how we use traces to understand the request timeline. The other thing you can use is below the header we see these spans in our request, right? The first time we looked at these spans, one of the things we saw was we saw two identical spans, right? So one of the things traces can tell you is if you see two spans with the same name close to each other, that is a sign of duplicate computation. So in our traces, we saw two spans, like it's called count boards followed explicitly. There were two calls. And when we looked at the code, we actually realized that because of a weird structuring of the code, the call was being made twice. So we refactored the code and we only made the call once. And this actually solved two problems for us. This gave us double benefit. First benefit was it reduced the home feed latency by 20 milliseconds, right? The second big benefit we got was our latency improved, like the number of calls to our backend service were cut down in half now. So we were only spending half the amount of resources while we improved latency like 5%, right? That's a double win for us. And traces are really good for understanding like these weird things which you just can't catch with a code review or just looking at logs, right? Then we also wanted to use traces for debugging, right? So let's say you have a debugging. This is a common scenario. Somebody pushes out a new version of the code. Something is slow, and let's say a memcache call was slow, and we want to know which memcache cluster we are hitting, so they can go look at the memcache cluster's dashboard or something, right? And understanding which memcache cluster we were hitting was very hard. So very hard because it was in some memcache log which the SRE team does not have access to or don't know where it is. So usually the communication, like somebody pings like the service owner in Slack, service owner is like, hey, I don't know, let me ask the memcache team. They ask the memcache team, and then somebody from the memcache team replies to say that, hey, like it's using this pool, right? And every time we were rolling out new pieces of software, this was slowing us down, just getting information. So what we did was we instrumented the memcache client to actually capture the pool name, the keys, and the result along with the duration it took. Once we did this, every time they had a question, they would just go to a trace, click on that request, and see which pool the request hit. Okay, so this was very useful from a debugging standpoint for our developers. So the other use case is we also use traces to tune our distributed systems. So one of the things traces are really good for, and it's a textbook example for traces, is understanding whether whether a computation is serial or parallel, right? So the way you would understand this is you look at a trace, okay, and every time you see a step pattern like that, right, like the top image, it means that you have a serial execution. But just because you have a step pattern, it doesn't mean that's an opportunity for parallelization, because the computation inherently can be serial, right? But in this specific case, memcache calls were all supposed to be executed in parallel, but the getMany call was always executed serially. We didn't know why. So when we looked at the code, we realized that memcache client had multiple APIs for each call, and all those APIs had a decorator in Python which would make the call run asynchronously. But the developer forgot to add that decorator to the getMany call, so the getMany call was being executed serially. So once we went in and added the decorator, all our getMany calls were parallel, and we shaved off about 5 to 10 milliseconds from our home feed load time. So the other thing I'm very excited about for traces is we want to reduce the time to triage, right? So one aspect of that is debugging. The second aspect of it is, let's say something is slow. You want to know why it's slow, right? And that takes an awful amount of time today. So what we tried to do is we took our metrics and we married them with our traces, and this is how we did it. So we have our metrics dashboard, right? For example, this graph here shows the amount of time it took to serve the v3 get board API, right? So that's the graph that shows latency. Then we married our traces. This is how we did it. So we have those, you see those red dots there? Those are the information from our tracing system, and each of that red dot is a trace. So what you can do now is you're looking at this graph, and then at 9 p.m., right, you see that there is a spike in latency. What you can do is you can go to the red dot at 9 p.m., click on it, and it will take you to a trace, and hopefully that trace will tell you why we are taking longer, right? You can clearly see where the time is going. You click on it before one and after one and just compare, right? And this was very useful for us because this increased our tracing, the adoption of tracing. People saw immediate value in how a tracing was useful because it was in context. And this was very useful for us because developers were like, okay, what is this? I'll click on it, they see a trace, and they're like, oh, wow, okay, now I know what's going on. So this helps them reduce the time to triage because they look at a graph, they click on a button, and hopefully they'll get the answer. Then one of the recent big projects we are doing at Pintrace is actually running our service across multiple AWS regions. So we wanted to do that, and typically the first step when we are running a service like that is we need to figure out the order in which we have to deploy the services. The reason this order is important is because when we are deploying these services, we need to deploy all the dependencies first before we actually deploy the service. So we use the before tracing existed, this was like the work for some senior engineer who would spend like a month figuring this out, right? But with traces, we were able to generate a service dependency graph. This one shows the service dependency graph overall, but then we were also able to generate a service dependency graph per API, so we could figure out the order in which the services could be deployed. Another use case for our tracing is we care about, this is the first thing I talked about, which is we want to understand how a request is executed, right? And when we want to understand how a request is executed, what you're actually asking is, I clicked this button and then something showed up, what happened in between, right? That's what you want to know. And so we started this new project called end-to-end tracing. What it is we wanted to trace a request from the Android client through the CDN, through our backend Python and Java services, all the way down to a database call, right? That's what we want to do with end-to-end tracing. And here we just finished getting all the pieces deployed to production. And here you can see a trace where an Android user clicks on a pin, and then we can see a request through the CDN through NGAPI, which is our Python backend, to pin and board service and memcache and all the other services which are in Java. So using this, we can get a complete picture of how a user request has executed. So just yesterday, we also instrumented our JS client to actually capture the browser events as a trace and put them into Pintrace. So one of the things that came out of this project was this is pretty cool, because now we can see how the user actually saw, how the user actually perceived the latency, or how the user used our service. Not only that, we realized that we were computing user perceived latency wrong. Like, our measured latency was pretty much somewhere between like 1 to 2 seconds slower, like faster than the actual latency. So this was a big lesson for us. By putting this data in, we were able to see that our end user latency was much higher than what we thought it was. And one of the bigger problems was, even before, when we were tracing the clients and the backend, we didn't have any insight into CDN. So the CDN told us, hey, like, this is the latency we see, and the client side, we looked at the client side latency, we looked at the server side latency, like nothing added up. So what we did was we wanted to trace through CDN. So what we did is we took all the trace headers and made them as part of sent them as part of CDN requests. And later, we would parse out the CDN logs from Fastly and ZXs and generate spans and add them to Pintrace with all the CDN metadata. And using this information, we were able to answer a crucial question. We were able to answer, hey, is this trace because of network? Was it because of a slow network? Was it because this guy was on a mobile phone in a third world country where there is no good remote connection? Or is it because of a fundamental problem in our clients? We were able to answer those questions. And now we are using this data to perform global CDN traffic analysis to understand user perceived latency much better. One thing we realized from the logs is, even though the CDN logs say, hey, like, it only takes 500 milliseconds, we saw cases where it was taking multiple seconds to do a round trip request, and we don't know why. And the outcome of the CDN traffic analysis for us is it provided more questions than answers, but at least now we know what questions to ask. So going forward, we have several more applications of trace data. We wanted to further improve the time to triage by providing automated root cause analysis, understand our P99 latencies better, understand where they're coming from, which layer of the stack they're coming from. We want to understand architectural optimizations. For example, one of the things we saw in our data was when we load a home feed request, we make a request to ads. And the ads request is pretty much the last request to finish in the home feed execution. And what we realized is we were making the call about 100 milliseconds roughly into the call. And what we realized was if we just made that call sooner, we would shave off those 100 milliseconds of the entire home feed request latency. And it was like literally moving a statement from like one line to just a few lines above in the code. And that shaved off like 100 milliseconds in our home feed latency. That's like 20% of the overall latency. We also built a latency pipeline. Today, a lot of our developers want to capture the latency of a variety of things. They want to see the breakdown of their latencies and things like that. Previously, they used to use their custom JSON formats, and they wanted to use a Hadoop job to process this data, store this data, and to analyze and visualize the data. But what we told our developers now is, hey, if you have this use case, just write that data as a trace. and just use and write it to our Pintrace backend. So we'll do all the processing and storage for you, and you don't have to do any work. So we are gradually moving some of those use cases into this pipeline, and that project is called a latency pipeline project. We also use the trace data to do some inter-AZ traffic analysis. We wanted to see, hey, answer questions like, hey, how bad is it if my request was going to a different AZ? Am I impacting the latency 1% or 10%? We don't know. And we are using the trace data now to answer questions like that. So here are the lessons learned from our work. The first thing, as I said before, is user awareness and education is very important to make tracing successful in the company. Most people don't realize that they can use traces to solve a particular problem. Once they realize that and they know how to use the tool, they'll just automatically use it. You just need to create that awareness. The second thing is, whenever you're building this tracing infrastructure, you need to begin with an end in mind. You need to know whether you are doing tracing to understand how the whole thing works, or whether you want to do an ongoing performance tuning, whether you're using tracing for debugging, or whether you're using tracing for a service dependency analysis. You need to begin with the end in mind, because the pipeline you build and the decisions you make when building those pipelines are impacted by what you want to do. And the other thing you need to do when you're doing distributed tracing is you need to trace the most valuable paths in the application. Right now, most people just trace everything, which is good, but getting there may be a time-consuming process. But if you only trace the most valuable paths in your application, you'll get more value out of your traces. The other thing is distributed tracing landscape can be very confusing. There are lots of projects. All the documentation is kind of scattered around. So just do your research before you pick one framework over the other, or just see what people did before you decide to go one way or the other. And finally, the quality of traces is far more important than the quantity of traces. Most people make this mistake of, hey, I want to trace more requests, or we want to trace more data. But what I've seen is as we have seen, a single trace can tell us a lot of stories. And so if that single trace or that handful of traces that you capture are of high quality, the value of your traces is much higher than tracing a lot of requests. So in the end, quality of traces is very important. So this, we have started this project alone, but over a period of time, several people contributed to it at Pinterest, and we have written several blog posts about it, and thanks for attending.
Right, do we have a quick question or two? I have someone walking really quickly to ask a quick question. So a quick walk for a quick question. Here we go.
So I'll bite on the obvious question. You say quality is better than quantity. How do you pre-assess that a particular trace is going to be a good quality one?
You can pre-assess, but once you see the trace, basically you'll know whether it's the data in there is good or not. Like when you look, once you start your tracing, you would know whether the trace is complete or if it's missing information.
We'll visit this offline.
Okay.
What was the excuse me? What was the aha moment when it came to deciding that you needed to build this tracing system to begin with?
The aha moment was we were trying to do when we started doing the manual tracing project. We were doing the same thing over and over again, and we wanted to democratize that process of, hey, like we wanted to understand what is happening, and that was the moment we were like, okay, we should do distributed tracing now.
Thank you.
Hi. So is there a registration process for services, like to register with Pintrace? And what's the overhead? Because what I see, like a lot of teams and services are shy of, oh, there is an overhead to register and get through this process, even if it will benefit in long term. So
I see. So we don't see, in terms of registration, we don't have anything like that. If you use the company's service framework, the request is automatically traced for you. You don't have to do anything else.
Okay.
And in terms of performance overhead, it's negligible. It's like 1% or less than 1% in most cases for us. So yeah, there is literally no overhead.
So you made it easy to onboard.
Yes, yeah, that is very important.
Okay.
Yeah.
All right.
Okay, one more question.
You mentioned that you had to instrument all the different permutations, which could be a long time before you get value. Could you just do like the top couple layers and build it iteratively where you get deeper into your stack and still get value to start up?
Yes. So if you're a startup, my first advice if you want to use tracing is to use a framework that's already traced. That's the best way. But if you have to build it, build it depth first manner, as you pointed out. Yeah.
Okay, thank you, Suman.